Let's stop for a moment and let's look back at our journey. So, we are discussing the supervised machine learning process. In that, we are in step 4, which is feature engineering. In that, we have completed the feature selection. So, the feature selection can be done using univariate selection, using statistical tests such as z-test, t-test, chi-square test, or ANOVA or f-test. And after that, we have looked into the feature selection using feature selection algorithms. So this can be classified into three: either filter type feature selection such as variance, threshold information gain, or wrapper type feature selection such as recursive feature selection, recursive feature elimination, forward backward eliminations, and embedded type feature selection such as lasso rich, L1 L2 regularization terms, and elastic net, which consists of L1 L2 both regularization terms. So then we have moved on to the feature extraction techniques. Under feature extraction techniques, we have started with the dimensionality reduction methods, where we have seen PCA, principal component analysis, LDA, linear discriminant analysis, MDS, and multidimensional scaling, and T-distributed stochastic neighbor embedding, TSNE, and autoencoders. So this is what we have seen. Fundamentally, these dimensionality reduction methods can be used in feature can be used under feature engineering, and also can be used in EDA, exploratory data analysis. Not all, specifically linear discriminant analysis, or TDSN. So these can also be used there to explore the hidden patterns. However, this can also bring the high dimensional data into the lower dimensional space. But the negative side or negative aspect of this is very less amount of explainability and interpretability of the data set. So now it's time to move on to the data transformation. So here we will be discussing normalization, standardization, log transformation, and data encoding. So this is also comes under this feature extraction. So here we will convert the data, maybe categorical variables, into a numerical variable, into numbers, using various encoding techniques. Or sometimes you have a numerical variables that you can standardize or normalize, or sometimes you do the log transformation to that data to use as a feature. So these are the techniques we will be covering up now. So it's time to begin a data transformation under feature extraction in step 4 of feature engineering of supervised machine learning algorithm. So with this, we have come to a question that what is a data transformation? Data transformation is the process of converting or changing the structure or characteristics of data to make it more suitable for analysis, modeling, or visualization. It involves applying various mathematical, statistical, or computational techniques to modify the data in order to improve its quality, consistency, or usability. A data transformation can be an important step in the data pre-processing stage of a data analysis or machine learning pipeline. I will repeat this again because this is very important aspect of data science or machine learning project. So data transformation can be an important step in the data pre-processing stage. Data pre-processing stage of a data analysis or machine learning pipeline. as it helps to address the issues such as data normalization, scaling, encoding, handling missing values, and dealing with outliers. So the main goal of data transformation is to prepare the data in a format that is appropriate for the specific analysis or modeling techniques being used. So this is the vital step in the machine learning pipeline or artificial intelligence project pipeline. So that's the reason. So in this, what we are going to do is, so it helps to address issues such as data normalization, scaling, encoding, handling missing values is called as imputation, and dealing with outliers, we call that section as data outliers. Okay, so the main goal of data transformation is to prepare the data in a format that is appropriate for the specific analysis of modeling techniques being used. So now it's time to get into the first technique of data transformation, which is data normalization. So data normalization is the process of scaling data to a common scale in to a common scale or range in order to remove differences in the magnitude or units of the data. So common normalization techniques include min-max normalization, G-score normalization, decimal scaling, root transformation, and a log transformation, which would be a separate case. So these are the four common normalization techniques. Okay, so I just want to reiterate what is a normalization. Data normalization is a technique used in data mining to transform the values of a data set into a common scale. That's why we call it as a normalization or normalized. So this is important because many machine learning algorithms are sensitive to the scale of the input features and can produce better results when the data is normalized. So there are several different normalization techniques that can be used in a data transformation of a machine learning model. So the first one is a min-max normalization that you can see on the screen. So what is min-max normalization? So this technique, a min-max normalization technique, scales the values of a feature to a range between a 0 and 1. This is done by subtracting the minimum value of the feature from each value and then dividing by the range of the feature. We will see that. And after that, we have G-score normalization. So this technique scales the values of a feature to have a mean of 0 and a standard deviation of 1. So this is done by subtracting the mean of the feature from each value and then dividing the standard deviation. This is what we call it as a G-score normalization. Then we have decimal scaling. The decimal scaling, this technique scales the values of a feature by dividing the values of a feature by a power of 10. Then we have the root transformation. So this technique applies a square root transformation to the values of a feature. So this can be useful for data with a wide range of values, as it can help to reduce the impact of outliers. So it's important to note that normalization should be applied only to the input features, not the target variable. Again, I'm reiterating, it's important and vital to know that normalization should be applied only to the input features, not the target variable. And that different normalization technique may work better for different types of data and model. So normalization is an important step in data transformation of a machine learning model. So it can help to improve the performance of machine learning algorithms by scaling the input features to a common scale. So if you take a simple example, let me put it here. So I'm going to write this as normalization. Yep. So let's take a small example. Normalization is used to scale the data of an attribute so that it falls in a smaller range, such as, I'm repeating that, normalization is used to scale the data of an attribute so that it falls in a smaller range, such as -1.0 to 1.0 or 0.0 to 1.0, 1.0. So it's generally useful for classification algorithms, but this is what is a normalization means. So now the next question that arises in our brain is, what is the need of a normalization? Normalization is generally required when we are dealing with an attributes on a different scale. Otherwise, it may lead to a dilution in effectiveness of an important, equally important attributes. So because of other attribute having values on larger scales, in simple words, when multiple attributes are there, but attributes have values on different scales, this may lead to poor data models while performing data mining operations or machine learning algorithms or models. So they are normalized to bring all the attributes on the same scale. Let me see this example. You have years of experience, which is just tens of data. It's tens, that's it. So either single digits or double digit. Even if it is double digit, maximum it can go up to 25. But here you can see that you have 10, 7, 5, 6, 8, 15, 7. Most of them are single digit and 2 are double digit. When you see the salaries are more than 5 to 6 digits. So minimum are 5 digits and more than that. Now, these two attribute values are at a different level. The attribute salary and year of experience are on completely different scale, and hence attribute salary can take high priority over attribute year of experience in the model. Now to suppress this behavior, we need to do something. That something is nothing but the normalization, where you can bring down the year of scale, this year of experience and then salary to the same scale. That could be either 0 to 1 or -1 to 1. That's it. It's a normalization. For that, we can use decimal scaling or min-max normalization or G-score normalization or zero mean normalization.